I'm Syamil, currently majoring in physics at Faculty of Applied Sciences UiTM Shah and going to guide you through one of this degree's core subjects, electricity and magnetism.
Physics is the laws of the universe and math is the language we use to write it. So before diving into electromagnetics, we must understand the language to speak it, which is vector and coordinate. Let's have a quick refresh. Vector is a quantity with both magnitude and direction. Unit vector is simply only the direction of a vector scale, so its magnitude becomes 1. Magnitude is found by finding the length of a vector by applying Pythagoras theorem. As you can see, adding two vectors gives a resultant vector. The dot product tells how much one vector points in the same direction as another, important in finding flux through a surface, and the cross product gives a new perpendicular vector to two vectors. A direct example where we just add two vectors, then we use cos theta and dot product to find the angle. Different coordinate systems help simplify problems by matching the geometry, aiding calculations in concepts like Gauss's law. Also, wires match cylinders, point charges match spheres. We must know how to convert these points and unit vectors between systems using these formulas. The del operator uses partial derivatives in different systems to find gradient, divergence, curl, or Laplacian of a function. The gradient is simply the steepest path at any point towards the peak. The curl and divergence measures curl and divergence respectively at any point, while the Laplacian measures how much the value differs from the average surrounding. Let's look at this wave function and visualize it and have it in our minds. Next, let's see this del operator visualizer app I designed locally on my laptop. You can see the curl is a vector quantity with arrows, and gradient is also a vector quantity where you can see the arrows point towards the peaks, like where you have to walk at any point to get to the peak. Then the divergence is also a scalar value that measures how much field vectors diverges from that point. Higher divergence means more field vectors diverges, while the Laplacian is sort of local max or mean, or shows smoothness of wave, which is also a scalar. Now let's take this peak of the wave and look at it from above. The gradient will have vectors pointing from many points towards the peak. Therefore, at that peak, divergence will be negative as many vectors converges towards it. And from this gradient is also how curl can be measured. Or you can see these arrows will bend at some points, like here. And that is where a swirl will happen, and that is what the curl quantity measures. Let's look at a very direct example question, where we just have to use the formula of gradient given and then sub in the value of the given point, as shown here. Now let's get into the real physics. In static electric fields, first we must understand interaction between charges. The arrow represents strength of attraction or repulsion depending on polarity. Notice how the arrow lengthens as they get closer. That's electrostatic force. Then let's take out the negative charge. The positive charge still produces arrows, which is the electric field, and a point further from it will feel less strength. We can know the direction of electric field if we put a theoretical positive test charge. If source is positive, then test charge will always move away from the source. If source charge is negative, then the test charge, indicating the electric field, is moving towards the source. So, Coulomb's law states that F is inversely proportional to R squared. From that, we can find E from source by dividing the test charge. But what if the source is not a single point but continues along a line, surface, or volume? That's where unit vector comes into play, and we also have to use the differential element of source charge. Now let's look at this example question, where the ring acts as a source charge and there is point above it. To find the E from the ring at this point, first find vector from source to point. And the vector is negative AP direction in the radius and positive HAZ direction. Since source is a line, so dq equals line density times dl. And dl is the arc of a circle, which is AD theta. And when solving, we can cancel out the AB direction because at every point it cancels each other out, so only AZ remains. Integrate with bounds from 0 to 2 pi for a whole circle, and you'll be able to prove it. Just now we visualized electric field as arrows. Now let's imagine lines. So at every point there will be a line of electric field coming out of the source charge. Let's put a sphere around it. There will be lines passing through the surface at every small area dA. So what about the lines passing through all the other areas? Integrating E dot dA over a surface, over the whole surface, counts the total number of field lines passing through the surface, which is the electric flux. Gauss' law said that the electric flux will equal to the Q enclosed. This is a special case for symmetrical problems where source charge inside surface is symmetrical. This is Maxwell's first equation. Who's Maxwell? We'll see later. Let's look at this question. The source charges are made of a point, line and sheet where the latter two extends beyond the sphere. To find total electric flux passing through the sphere, we can use Gauss' law as there is symmetry. Simply find the total charge only inside the sphere. So the point charge, the line charge only for 8 meter length in the sphere, and the sheet charge, which is a circle of a radius 4 meters. After finding the charge of those three sources, simply add them up to find the electric flux.
One source of magnetic field is the steady current. So if a current goes up, that will be the thumb, and the magnetic field that swirls around it will be represented by the fingers, the right-hand grip rule. So imagine current going out of page towards us. So the magnetic field will be anti-clockwise as shown.
H is the strength of curl of magnetic field around a current at a point, and Biot-Savart states that H is directly proportional to differential current element and the sine of angle A, and inverse to its distance from current. The vector from point to current is used. A Gaussian surface around a current sees no net B flux because B runs parallel to the surface. The magnetic field does not pass through it, it just circles round, so magnetic flux is zero, Maxwell's second equation. Instead, we use Ampere's law, sum of H along any closed path equals the closed field current. This is one part of Maxwell's third equation. Let's look at C. To evaluate, first find unit vector and differential current element similar to finding E for a ring, but difference is we have to find the cross product between them first, then integrate from 0 to 2 pi for a full circle and sub in the values. Before we look at the electric fields from static charge and the magnetic fields from steady current, now imagine a loop made of conducting material. Within it, place static magnetic field through it into the page. Nothing happens yet. But if the magnetic field changes with time, for example, number of field lines increase, there will be an induced current that opposes the direction of the field. Why clockwise? Still using the right-hand grip rule, you'll see that in the loop, the field lines will go out of page. We can ignore the field lines into the page out of the loop, because what matters is inside the loop, the magnetic field lines created by the induced current opposes the original magnetic field. What if the magnetic field is still static? We can still create an induced current by moving the loop. So let's see. There is the static magnetic field, and we move the conducting loop through it like this. This will also create an induced current in exactly the same direction as we see just now, also using the right-hand grip rule. What's important is the created magnetic flux opposes the original magnetic field lines. Faraday's law states this, which is EMF is the rate of change of B flux in loop, which is Maxwell's last equation, and these are formulas for each case. This is a classic question. Use Faraday's law, first static loop in changing field. Integrate B over dt over the area, dx dy, and sub in the time. For moving loop in static field, find cross product of u and v, then integrate over dx. So who is James Clerk Maxwell? A Scottish physicist who during the 19th century formed the unification of all electricity and magnetism. Along with his equations derived in both integral and differential form, he proposed they are all interconnected aspects of one electromagnetic field.